Hello, 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 and welcome back to Shiksha DaCosta. Today we're going to learn about the cosine law as part of trigonometry. So in this lesson, you're going to learn what the cosine law is. We're going to prove it algebraically together. You're going to find out the situations when you can use the cosine law and exactly how to do so. And you're successful, of course, by the end of this lesson when you have successfully explored how the cosine law was developed, specifically with acute triangles. To start us off, see if you can find the distance from point A to B in terms of P, Q, and X. Pause the video here and take as much as 15 minutes to do that. Okay, well, if you are a little bit stuck or if you are able to solve it, hopefully your solution looks a little bit like mine. So the way I decided to tackle a problem like this is I know that I'm trying to get a point from here to here. Now I recognize that this is a cube. It's a 3D shape. And therefore this line is actually going through the inside of the cube. And I can't really it doesn't really have anything in common with any of the side lengths of the cube. But if I sort of draw a line from point A to this corner here and then up to point B, that right there would be the length of X. And this would actually be a right triangle. It doesn't look like it on my sort of two-dimensional drawing. But if you imagine that this is a cube, then the red line is going across the floor of the cube, and the green line X is actually pointing straight up out of the floor at exactly 90 degrees. So that is the sort of triangle that I'm talking about here. And that triangle I might redraw on the side as a right triangle. Now we've done a lot of work with right angle trigonometry, and one thing we know that in a right triangle, you need at least three pieces of information, just like in any triangle, to be able to solve it. I know that this angle here is 90 degrees, and I know that this side is x, but do I know anything else about this triangle? No. I don't know what these two angles might be, and I don't know what these two side lengths might be. So I guess I'm kind of stuck here, aren't I? If you are able to get unstuck, pause the video here and see if you can get unstuck if you're in the same position as me. Well, one way that I decided to tackle that is to say, okay, well, can I actually find out any information about this angle or these two sides? And just looking at here, well, the pink side is the side I'm, going to end up with. That's my final answer. So is there a way for me on the way to that to find the length of the red side? And in fact, there is. If I look at the floor here, there's actually another triangle going on right there at the bottom of this. I called it a cube, but I guess technically it's a rectangular prism because I don't know any of the side lengths. And this right angle triangle, which is sort of on the floor of this rectangular prism, has side lengths P and Q, and its hypotenuse is the same as this red line here. So if I want to find the pink line, I first need to find the length of the red line. And to find the length of the red line, well, I've got a right triangle. I have the legs of the triangle. And to find the hypotenuse, there's a theorem that's quite famous. You may know it by Pythagoras' theorem, but I actually know it as Bodhiana theorem. Bodhiana was a mathematician in India, and he wrote basically the following hundreds and hundreds of years before Pythagoras was ever born. And he said that in a right angle triangle, the square of the hypotenuse, which is the side opposite the right angle, is equal to the sum of the squares of the other two sides. Now, of course, he didn't write it in English. He wrote it in Sanskrit. But this is essentially what he was saying. And you know this as a squared plus b squared equals c squared. Now, this relationship, which is something hopefully you have some experience with, you can use to find the length of the hypotenuse. That is represented by c here. In my triangle, the way I would calculate c is, well, I know, let's say that a is p, b represents this side, which we've already assigned the letter q. So if I want to find out what the hypotenuse is, I obviously have to isolate that variable. It's not isolated right now. It's got a 2 up here, a square. And to isolate any variable, I always do the opposite of any operations that are happening. What is the opposite of the operation to square something? It's actually to take the square root. Opposite operations, as you know, will cancel each other out. And of course, you also should know by now that what you do to one side, you can't just leave it like that, otherwise it's no longer equal. You have to do it to the other side of the equation as well. And so now I end up with an expression that I can use to calculate the hypotenuse here. It would look like something like a squared plus b squared, all square rooted. Well, here in this case, I've assigned, this a value. This sort of represents this side, which I've already given the length p. So this would be something like p squared plus q squared, all square rooted, would give you this length right here, which is represented by c. And so I'm going to write that over here. This is the length of this side. If I knew actually what values p and q are, I could evaluate this. But since I don't, this is about as simple of an expression as I can use to represent that side. And the reason that we wanted this side represented is so that we can plug it into basically the same formula for this triangle, right? This side length is the root of p squared plus q squared. And if we use the exact same formula here, one side would be this, the root of p squared plus q squared. That all should be squared, plus the other side being squared, and you've got that here, plus x squared. All of it square rooted should give you the length of the hypotenuse, which in this case is this side right here. So if I were to plug that in here, notice I've got a square root and a square, and just like here, those two will cancel each other out. And I'll end up with the expression for the hypotenuse being the square root of p squared plus q squared plus x squared. Now this is all neat and all, but what does this have to do with solving triangles? We already kind of knew the Pythagorean theorem or the Bodleiana theorem, right? So did we really learn anything new in this? One thing we certainly did learn is how to calculate the length across from one corner of a rectangular prism to the other. It's simply the sum of the squares of all the side lengths, all square rooted. But something else we learned was basically how to take a variable and express it as an entire expression. And then we can use that entire expression as the variable in another expression where we have to replace it. And that skill is going to come in really, really handy in just 1 second. Do you think you could find the height of triangle ABC? In this case, the height might be a line sort of extending, if this was the base, that meets the base perpendicularly. If you can, see if you can try and find an expression that would help you calculate the height. But I think you might find it pretty tough. Either way, give it a shot, pause the video, and see how far you get. Well, one way to tackle this is to, first of all, obviously draw that line there that does meet the base at a 90-degree angle, and this would be the height of the triangle. Now, I could have drawn that line from here to this and said that this was the base, or even from this point across to here and said that, side C was the base. So the orientation of the triangle doesn't really matter at all. We're trying to find out this length right here, right? From point B to, I'll call this point D. This is the height of triangle ABC. Now, very similar to how the sine law is formed, one thing you can recognize right here is we've actually split this triangle into two separate triangles, both of which are actually right triangles. There's one right here, and there's one right here. And we're going to try and find the height of this triangle using Bodleiana theorem. Now, recall that Bodleiana theorem tells you that the sum of the squares of the legs of a right-angled triangle is equal to the square of the hypotenuse. In other words, a squared plus b squared equals c squared. The problem is in this triangle here, I have one side here, the hypotenuse. I have this side here, which is a side length, but I don't have this side. And similarly, in the other triangle, I have the hypotenuse. I have one side, which is the height, but I don't have this side here. So I'm going to do something kind of interesting. I'm going to say, let me just say that this side over here is just x. This side over here, I could assign a new variable like y, but I recognize that depending on whatever I choose for x, or whatever x ends up being, this distance will be able to be calculated. We take b, which is the entire line, and we subtract x from it. So that this side is just b minus x. So let's take a look at our triangles. This one on the right here simply looks like this. This is triangle BAD. And by Bodiano's theorem, if I take the bottom, which is x, and I square it, and I add the other side length, the other leg, which is h, and I square it, I should get this side, which is side C, squared. And so that's sort of how I might replace these variables with the variables from the actual triangle in question. On the other hand, with the other triangle, this yellow one right here, this is triangle BCD, the Bodiano's theorem might look quite different. The first leg of the triangle has a side length of b minus x, so I'll take all of that and square it. And then I'll add this side, which is h, and I'll square it. And that should equal the hypotenuse, which is a squared. Notice that whenever I replace a variable, I always put brackets around it. And that's a very, very important step. Without these brackets, it might seem like this square is only being applied to the x instead of being applied to the entire expression b minus x. There's one more relationship, which I'm going to point out to be true here, and that's from this triangle right here. Looking at this triangle, I have this angle here. I can say that this is the adjacent side, and this is the hypotenuse. And so that's one of the statements that I know to be true. Cosine of this angle is going to be equal to x over c. Now, I could have brought up the sine and tan ratios. So why did I only bring up the cosine one? Well, all things in good time. That bit will certainly be made clear why I've done this in just a second. What I'm going to do here, and again, this won't really make sense until after I'm done, but of course, we're going through something that's very complicated called a proof. And very often in a proof, it's not exactly clear why you're doing something until after, the mathematician has already shown it to you. And in this case, I'm going to take this expression, and I'm going to do something that I'm definitely allowed to do. I'm going to multiply both sides by the denominator, because I'm just going to try and isolate x. So one way I can calculate what this distance is I can take this side and multiply it by cosine of this angle. Okay, one last thing that I'm going to do is I'm going to go back to my Bodiano's theorem right over here, and I'm actually going to isolate h squared because I see there's an h squared in this equation, and I'm going to try and replace it with an expression that it's equal to. So over here, if I subtract x squared from both sides, I find out that h squared is equal to c squared. Notice I've evaluated the brackets here, minus x squared, and I've evaluated those brackets as well. So if h squared is equal to c squared minus x squared, then I can replace h squared over here with the exact expression that it's equal to. Okay, hopefully you're following along so far. It's not clear why I'm doing these things, but certainly you can follow along that I got this expression from Bodiano's theorem or Pythagorean theorem. I got this one from the same, and I got this one is one of our known primary trig ratios. Why am I isolating these random pieces of them and putting one into the other? Well, if you look over here, this expression right here on the left-hand side of the equal sign is something that I'm going to try and expand and simplify. And you may not have learned how to expand and simplify something like this. This is b minus x squared. In other words, b minus x times itself 2 times. And one way to expand a binomial, in other words, an expression that has 2 terms, is to sort of make something called an array out of it, which is like a rectangle where you have the terms on the top and on the bottom. So this is a length of b. This is a length of negative x. This is a length of b. This is a length of negative x. And of course, the area of this rectangle will be b minus x times b minus x, the length times the width. And if I want to find the length of the area of this rectangle, I notice I've broken it up into 4 pieces, right? This piece has a length and width of b. So if I want to find the area of the full rectangle, I can find the areas of each of the rectangles inside and add them all together. I know they look like squares, like I've just drawn it that way, but I actually don't know that b is the same length as negative x at all. They're just placeholders for now. Anyways, the area of this is b times b, which is b squared. The area of this is negative x times b, which is negative bx. Same with this. B times negative x is negative bx. And finally, our last quadrant of this rectangle, negative x times negative x is positive x squared. So b minus x squared, if I take b minus x and I multiply it by itself 2 times, the total answer is b squared minus bx plus x squared. I still have the rest of my equation to deal with, and I'm just going to leave it the way it is right now. Notice that there's a 1 in front of these brackets, so if I were to expand them, if I were to use the distributive property, the brackets would just sort of disappear, and then I can start collecting my like terms. And I actually have a few like terms here. I have a positive x squared, and I have a negative x squared, and those two will cancel each other out. I also have negative bx and negative bx, and this is, of course, negative 1 and negative 1, which together make negative 2bx. I have a b squared, and I have a c squared. The last thing I'm going to do here, the last time I'm going to substitute something in, and hopefully you can now see the sort of genius of all of this cosine law theory coming together. Notice that I've still got an x here, and I actually know what x represents, or another way to actually express x. It's c times cosine of a. And so I'm going to replace x here with c times cosine of a. And this, my friends, what you've got here is actually, I'm just going to rearrange the equation. This is called the law of cosines. I have a b squared plus a c squared minus 2 times b times c times cosine of a. 2bc cosine of a. And all of that is equal to a squared. What does all of this mean? The genius, if you don't quite yet see what I just called the genius of all of this come together, let me break that down for you. Basically, we have a equation here that contains all 3 sides, A, B, and C. A, B, and C. It also contains one more angle. So there's 4 variables being represented here, A, B, C, and angle A. And we can, if we know 3 of those, we can always find out the last one. The cosine law is as follows. A squared is equal to b squared plus c squared minus 2bc cosine of a. And that's a triangle that might represent that. There's actually another version of the cosine law. Instead of making the height over here from point B all the way to the side length B, if we instead drew it another way, if we went from point C over to here, we might end up with an entirely different expression. It would look very, very similar, though. It might look like this. To find b squared, we take a squared plus c squared, and we subtract 2ac cosine of the angle in between. It might also, if we had gone another way, look like this. All of these 3 are the cosine law all at once. Notice how there's similarities in their structure. The only thing that you have to keep in mind is that the side length on this side of the equal sign is opposite the angle that you're using in the question. Okay, so these 2 must match. Now, in all of these equations, the variables are all contained in them are all 3 sides and one angle. The angle does differ, so you have to choose which one you're going to use based off which angle is involved in the question. And so you can, because you have 3 sides and an angle involved, you can use the cosine law to solve a triangle when you have all 3 sides and you're trying to find any one angle. The cosine law can help you with that. Just plug in the sides that you know and isolate the angle. It can also help you when you have just 2 sides and you have the angle in between them. So if you have A and C, if you also have angle B, then you have everything on the right side of the equation here, and you can use it to find side length B. And depending on which two sides you have and the angle in between them, you can actually use either one of these two cosine laws as well. In triangle PQR, which I'm going to start drawing right now, right? So that's triangle. I'm going to label the endpoints P, Q, and R. Side P is 15 centimeters. So side P would be this one. That's 15 centimeters. Side R is 19. So that would be this one right here. And angle Q, which is this one over here, is 50 degrees. Now, in this case, if I want to find out the length of side Q, what I need, in this case, I would have, because I have two sides and I have the angle that is contained in between them, that tells me that cosine law is the right one to use. Okay, that will help me find the value of Q. So this is the cosine law. And if I'm changing these around, this is the side length that is unknown. That'll be Q. That means that this has to be P and this has to be R. I'll just write that down here. So that's P, which is 15. That's R, which is 19. The angle that is contained in between them is 50 degrees. And if I evaluate all of this by putting it into my calculator all at once, I'll find out that the length of Q is about 15 centimeters, 14.819 with some more decimals after that. Find the measure of angle A to the nearest tenth. So if we're looking for this angle here, and we actually have three sides of this triangle, we can safely use the cosine law to solve for it. The cosine law basically goes as follows. Now notice that I chose the version of the cosine law that has an A at the front and at the end, and that's because I know I'm looking for angle A. Angle A needs to be involved in my question, and so that's the only one I could have chosen here. And this one actually has to match it. So that has to be the opposite side. The other two sides go here and here. Okay. Now, if I want to find the angle A, I could start plugging in my variables and evaluating, but I'm actually going to try and maybe let's isolate A first, and then I can plug in my variables and evaluate. And to do that, I have to recognize I got to get angle A by itself, which means I got to get rid of any term that doesn't have the A in it first. B squared. Oh, I don't see an angle A in there, so I got to get rid of that term by subtracting it. That'll cancel it out, and I have to do the same on the other side. C squared, well, I have to do the very same thing. I'll subtract C squared on both sides. That'll cancel it out here. And that'll leave me with A squared minus B squared minus C squared, all equaling negative 2BC times cosine of A. All of this is multiplication, so I can actually divide them all, the entire side, by negative 2BC, and that will cancel out all this entire number here, as well as canceling out the division. And then, of course, I have to do the same thing to the other side. I have to divide this entire expression by negative 2BC. And now this is what I end up with. Notice I am getting closer to isolating A. The last step I'm going to take is I'm going to do the cosine inverse, and that will cancel it out on this side. And then I have to do the same thing on the other side, leaving me with an expression like this. And this is actually yet another version of the cosine law. I've just rearranged it to isolate for an angle. And now if I plug in my known values 4, 7, and 6, I can now evaluate all of this all at once. I could do it one step at a time, or I can plug it into my calculator all at once. And if I do that, my calculator spits out the number 34.7719. To the nearest tenth, that would mean that angle A is 34.8 degrees. So the last thing to mention here is that if we take, for example, this first equation here and we rearrange it to isolate the angle, you get something that looks like this. And of course, you could have done it interchangeably as long as these two must be opposite side angle. So this is the side length, and this is the angle that is opposite it. And this is one way to use the cosine law to find the value of an angle if you would prefer not to actually isolate the angle every single time. My recommendation is you memorize this and you memorize one of these, Because as long as you remember that these two must match, and as long as you remember that the first and the last variable in these equations must match, the rest of it is actually pretty easy to just, plug into place. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.